Hello, everybody. So, plan for tonight is to finish up some of the list of talking about data structures. The general idea of them, see the basic overview of them. Those continuing on to like a 4-year pathway will have to take spend an entire semester on data structures. So going over the basic overview of them, the ones we're going to talk about tonight, our textbook has examples of them, and one of them is based off some math that y'all probably haven't encountered yet anyway through school. It doesn't usually show up till like 400 or 500 level math classes, so we'll just kind of draw a rough picture of it, maybe look at a database example of it. But in general, I was also thinking probably be kind of a short night tonight as far as lecture goes. I like to front load courses. That way, when we get near the end, there's time to a little bit more time to work on projects and stuff like that. But also this finishes up, well, we're in a 16-week course. So what is it? This finishes up with week 14, which means 2 weeks left. So also a good time to get, try to relax a little bit, because I assume everybody at 200 level course knows what the last couple weeks of a semester are like. They're usually a little bit hectic, right? So I was thinking to keep it, try to keep it short tonight. We'll probably only go to about the time that we would normally take our break. And yeah, then as normal, I'll be sitting around till 8:50 ready to address questions if you have them. But ultimately, my suggestion for the last time tonight is try and relax, because none of you are all learning your first semester. You know what the last 2 weeks of a semester get to be like. So taking a few moments to relax when there's something blocked off on your schedule and then suddenly opens up, I was thinking would probably be the best thing. But the reason I was thinking that is because this time of the semester, everybody's got lots of stuff on the to-do list. So it's also a good time to work on some of that. So continuing with what we were looking at the other day, talking about data structures, and really the places where we would start seeing advantages from using these different things aren't going to show up in a classroom. And, in a classroom, we have to fit within our time constraints, and we're usually not working with we don't have arrays with millions of items in them. And we don't have to, the time to loop through an array isn't on the human noticeable time scales for anything we do in a classroom. So the data structure, we just want the concepts so that you have a rough idea of them in the back of your mind as you progress further and eventually need to start worrying about these things. Again, it's going to be in the working career, not in the classroom. You have some idea of the differences, at least the different pictures on them. We were looking at trees the other day. We looked at a binary search tree. That's going to be one of your go-tos most of the time. It's really easy to implement. It's a lot like we did with the linked list. That's why I went ahead and showed the linked list. Only there's basically 2 pointers, a left and a right, and we organize less than this goes to the left and greater than goes to the right. And we don't really worry about what the tree is or anything. We might end up with some strange looking trees. I think the one we had the other day looks something like this. And if we look at that, I'll notice that it's a little bit heavy over on this side. And really the heavy part's in the middle. So another common thing we'll see that we can get some advantages of is a well-balanced tree. Which the actual technical name for it is 2 Russian guys, and it hyphenates 2 Russian guys' names, and not short Russian names either. Y'all have seen Russian names. Like long, even for Russian names, and there's 2 of them. I'm not even going to try to pronounce it. If you Google well-balanced tree, you'll see the technical name for it. In America, we just call it this, I guess. That's a lot easier. Most of the world calls it that because only a small percentage of the world's population can actually pronounce the two guys' names. But it has to do with, well, when we saw the other day with the binary search tree, when we go in order, that ordering we put to it, the in order traversal puts everything right in the natural sequence for it. But when we did prefix and postfix, then we got more of like a wavy action. We go to sort of a high part, and the prefix, we go to one of our numbers and then we walk down. And then we come back up to something in the middle or at the higher end and then walk back down. And same thing for a postfix, only we start low and then go up, and then we come back down and walk upward. So we end up with that wavy pattern. And when we're doing those, the imbalance in this tree can really show up. We lose consistency in that pattern. So having a nice balanced tree, or as close to balanced as we can get. Start off the bat, let's say we have 4 elements. Like the first 3, we can restructure stuff nicely. Right, we start reading it in, get a list like this, and just glancing at it, I'm thinking this one would probably make a better root. Because if we do this as the root, then all of this is going to spin down over onto this side as well. Actually, that wouldn't make a good root. This one would probably make a good root, because then this one's to the left. These would come over to the right, and off that we'd get these 2 on the left over on this side, and these 2 on the right over on this side. Then we have a nice balanced tree. But obviously we can't always balance it perfectly. Right off the bat, if we had 4 elements, 3 is going to balance nicely, but no matter where we try to put that 4th element, we're going to end up with an imbalanced tree. There's a little bit more on the right side there. So there's only certain numbers. And the key part on those, it's a lot like setting up a binary search tree to begin with, but we add extra criteria into our add method so that every time when we don't just find where it goes in the tree, we then reevaluate what would make the tree the most balanced. And it helps with those patterns for prefix and postfix searches, making it nice and even, or as close as we can, adjust it as close as we can, and balanced on the root, right? We could have a whole bunch of things in the middle or a whole bunch of branches going outward, but what we want to do is try to get as close as we can to balanced on the root. So 5 things on the left and 5 things on the right. However they fall in the actual tree structure would be fine. I believe our textbook has an example of those, but the big thing is it's just an extension on a binary search tree, and it's pretty much the extensions all happen in the add method. Because every time we add something, we want to shuffle it around and figure out what the best root would be in order to keep that tree sort of even and centralized and nicely structured. Which that nicely structured tree is the next one we're going to talk about, and it's where you've probably heard probably been hearing for a while. If you've had me for for classes, you would have been hearing it since the SDEV 120 class. I'm going to go ahead and raise this picture. Hopefully the name there makes sense, right? We have our tree might look funky when we just start throwing things in whatever order we get the data. We just want to reorganize it so that it looks nice. It balances around the root. In general, it's not going to provide tremendous advantage over a regular binary search tree unless we add in a whole bunch of selection structures to jump around that. When we have the pre and post fix and we're passing through the data in more of a wave fashion than like a straight line, a straight linear line. We can add selection structures and work with that pattern. And the closer we are to balanced, the better we can be at predicting what that pattern is going to be. That's where that really comes in advantageous. For most of our operations that we would be traversing the tree for, it's about the same as traversing a binary search tree. Just an extra step in the addition thing. And there's an example of it in the textbook. But with the nicely balanced trees, we do end up with what's almost our best data structure to work with. You probably heard the word before, heap. I grabbed the notes out of the blue thing. Everything in here. Nope, I don't see the thing I was looking for. Let me Google a number real quick to make sure I write it down. Okay. So the other day we were talking about efficiency and how things change as we add more inputs. And a heap is the data structure that we get a big O of 1. We don't lose any efficiency. If we go from 3 data points to 300 data points, it's going to be exactly 100 times longer. There's no extra overhead for having more data. But a heap is kind of hard to put together. It takes a lot of adjustment. It's not an easy one to work with. So it's a lot better than a binary search tree for the machine, but the program has to work a lot harder to put it together. That's why we use binary search tree that we looked at the other day and spend much time on. We get a nice balance because we have a really good minimal gain in efficiency, or a minimal gain in inefficiency as it gets large, and it's really easy for the programmer to work with. So we get good. It works really well on the machine and easy for the computer, so that's a good balance. Heaps are a lot harder to put together, but what it is I'll leave that up there. The good point of it, we don't lose any efficiency. Right? If we go from 3 data points to 3 million data points, obviously that's going to take more time to process. But it's exactly 1 million times longer. We don't have any extra overhead for the increase in input. And that's what big O notation is kind of measuring. And excuse me. What a heap is a complete tree with dual ordering. So kind of like the balance tree we were just looking at, we want it from the root, we need to make sure there's the same number of things on both sides, but that's not quite enough. That picture I just drew a moment ago, we could draw something like this, and that would be a balanced tree, but it's not a complete tree because there are missing branches here from being a complete binary tree. So we need to make sure it's a complete tree, a complete binary tree. So every node has 2 branches coming off of it. our root, and then each one, everything down, and then we'll always have pairs of leaves at the end. Any missing nodes are just filled in. I'll put it on one of the pictures I have here. And ordered left to right. So the dual ordering is tree ordering, that smaller things to the left, bigger things to the right. So we have that, but it also orders order left to right by level. Each level goes in order. And I'm taking out the word dual because it gets a little confusing. So instead of just the smaller things to the left, bigger things to the right, we also need to make sure that if we're on the second level here, everything goes in order left to right. Third level, everything goes in order left to right. But then it jumps out that our root must be either the maximum or minimum value element. Which that's why I went ahead and erased the dual ordering, because that kind of throws everything off. So we put it in a binary tree, and then whatever our maximum or minimum, largest or smallest element is, that gets swapped out with the root. So a couple of them here. I'll write some numbers in here for a minimum tree. I just wrote a few numbers here. So a 3, 7, 9, 6, 8, 12, and we'd probably write void in there. At this point, y'all haven't seen void used as an object, but it is an object we can use. But null is something we can assign. That's the version of nothing we can assign to things. And void is the version of nothing we can use. We have to have a full tree, so we can put a void object there, make sure we have a full tree, because it just fills out the tree. And the actual data contained in void at the electrical level, we just leave the electricity floating. We don't care what it is. So there will be something there. There'll be some ones and some zeros. So in a case like this, we could just pick a number between 8 and 12, put it in there, but really consider it void. We don't care what it is, just as long as it fits that pattern, as long as it fills out our pattern. So by void, something roughly like 1010 would work. Or if we write a whole byte, that would fit our pattern. It fit a 10 in there, but so there's a 10, our pattern's nicely filled out, but we're going to call it void, not 10, because we're not going to actually use this 10. It's not one of our data points. We just have to have a complete tree. And then however this was originally set up, once it was in there, the tree starts getting restructured, which there's a lot of steps to that. There's an example of it in our textbook. You can see there's a bunch of code about moving it to a balanced tree, finding the smallest element, moving that around, and then lots of shuffling until we get the right order. But you can see that it follows, well, after that minimum value there, 7, 9 go in order, 6, 8. I'm just going to stick with the void, but we would fill that in with a pattern and just ignore what it is, because we actually have to have something there. 6, 8, 12, things go in order that way. And we have the normal tree ordering, smaller things to the left, bigger things to the right, which would kind of mess up here.
So does that also go for like the fruit?
The root steps out of the root has to be the smallest or largest. So the other one, I have another one wrote down on paper that would follow the pattern. You see how this one causes a problem? Because smaller than 9, the next integer down would be 8. So there's nothing we could put there. So we just have to have basically binary gibberish in that spot to fill out the pattern so that we don't have any empty spots. But the root the root must be either the maximum or minimum. So we find either the smallest or largest. The other one I had was also only 3 levels deep. I'll do it in green. Oh, let's see. So on these, I picked 20 to be the largest element. 11, 15, 10, 12, 14, 16. So this one's actually full. So if we ignore that root, it follows all the rules for a tree and would continue down. We could come off 10 and, well, I guess there'd be a problem because those are close together. If we had more layers, more levels, we just want to fill them all in and follow this pattern so that after we get past that first row, everything goes in order as we move left to right, and everything past the root still follows that free pattern. And the biggest advantage here happens when we do postfix or prefix on a minimum tree or postfix on a maximum tree, because our root's either going to be with pre or postfix, our root's either going to be the first or last element. So that's why it has to be that. If we do prefix, node, left, right, we get 3, come to the left, 7, 6, then we go to the right, get 8. So it jumps a little out of order, and the order looks strange to us. You're used to order meaning number 1, 2, 3, 4, 5, 6, 7. We can change that around, right? We can go through and maybe I should say patterns instead of order. So there's patterns that develop that give us huge improvements when we put together this structure. And then use a postfix if we have the maximum tree. So we come all the way to the left and then come back. So we get left, right node, 10, 12, 11. Come back around this way. We have to go as far left as we can. Left, right node, 14, 16, 15, and then the 20. So you'll notice there's definitely 3 elements in that waving pattern that develops. And it becomes very predictable patterns, and it's sort of an optimal thing for a machine to go through. There's a lot of extra stuff involved with getting it in that order, though. I believe our textbook has an example of putting together a heap in Java as well. There's quite a few examples. But you've probably heard that word before and not really seen what the data structure is. So it's a special type of binary tree that has to be complete, and it gets this special ordering that not only is it the binary tree ordering for the most part, we also have, we swap our root out. It has to be the absolute smallest or largest in the data set. And then we start getting interesting patterns that are very, very predictable, and machines are great when we have predictable patterns. That's the perfect thing. So if we can very precisely predict what that pattern is going to be every time, the machine can jump around that pattern. That's why we get such great efficiency. The machine can spot the pattern and immediately jump to any data point on it. It doesn't have to, it can take the shortest possible route to any data point, which makes it really, really fast. What's on the next page? Oh, Hashtable. This is another one you've probably heard a lot of, especially since Hash has made it into normal English. This is how social media organizes their stuff. Well, we know the word. It's okay if I erase the heap thing. Does that kind of make sense? It's a lot of work by the programmer gives us a highly, highly, highly predictable pattern. And the more predictable a pattern is, the better a machine's going to be with it. So that's why heaps are really, really nice. And I believe there's an example of one in our textbook, code-wise. You can look at that. Take your time when you look at it because it's long, confusing code, and they try to put some optimizations in there. So there's a few lines where you really have to pause and think about it. You can't read it like an English sentence. You want to stop and think about what's happening on each line. And, also, it's built into our powerful programming languages like Java. We can just hash for a heap and use it. Somebody's already built one. So, like everything else, there's the basic idea is there, and we can just kind of ask for it. Kind of like we saw with stacks the other day. Wow, this marker does not erase for nothing. I can probably hear I'm starting to breathe heavily because I'm having to really scrub to get this black off the board. There we go. Now I can write the next thing. I just grabbed the black marker again, but maybe I could use a little bit of exercise. Next one's a hash table. A lot of programmers like to use dictionaries. Has everybody used a dictionary before? It's a map where our key value pair, where our key is a string. And essentially, we have different words for it, associated array, dictionary. But essentially what we're doing is we're indexing a collection with strings instead of integers. It's a lot easier for the human to work with. But that's going to slow the machine down, right? Because storing a string is supposed to, right? Our first index is age. That's 3 Unicode values, 16-bit Unicode values, 3 of them, we got 48 bits, versus our first an 8-bit integer or a 32-bit integer. If we use 32-bit integers, when we've used a 3-letter string, we're already bigger than a 32-bit integer. And that's probably a little bit short for a good key in a dictionary. And it's we usually want more than 3 letters. So there's a lot of overhead involved there. But it's really, really nice for the human to be able to work with that. So we need a way to transfer that. So a hash table is key value, a key value pair store. That's what I wrote in my notes. Collection, a way to store our data, and we index it with keys, which the catch-all term is a map. We can use any sort of object as our key. But what people use most often is going to be a string, just because that makes sense to us as humans. We use words when we communicate, so it's nice to use words when we write our program. But any sort of object would work. So a key value pair store where the key passes through an encoding algorithm. would I put here? To create a row index for a table. Create a row index for a table. Yeah. So I drew a little picture to kind of represent that. So in our code, we're going to write things up with keys and values. I'm just going to put it like a table here. Y'all know what it looks like in code, right? Different language to language, but we have some sort of string representing it. So maybe age 32. What else did I put here? Weight 133. And height 68 inches. So reasonably average measurements. Somebody that's 5'8", weighs 133 pounds, age 32. We need to store this, but using these, we're losing a lot of efficiency. And well, if 3 data points, it's not a big deal. But if we had integer indexes like a normal array, then we're using 32 bits on each one. But here's age. 3 Unicode values is already up to 48 bits. 1, 2, 3, 4, 5, 6. So 6 times 16 is what? 64 plus 32 is 96. Yeah, 96. So we're using 96 bits for something that an integer could easily handle. What 6? Yeah, same thing again, 96 bits. So 48 plus 96 plus 96 is that 250 minus 2 minus 8. 250 minus 10, 240. That took me a long time to do that math. 240 bits for something that 3 integers should be able to handle. 3 times 32 is how much? 96, right? So either one of these keys by themselves, we could index all of those with that same amount of size. And there's only 3 things in that data set. Okay? When it's up to 3 million, that's going to be a huge number. We're going to be up to gigabytes of extra bits just because it's easier for us as programmers to use strings. So what we need to do is come up with a nice little algorithm to turn those into integers, and then we can store it in a table. And the algorithm is called a hash. So here for the picture, I just drew a big bubble, right? Some sort of math equation, maybe something like a parabola. 3x squared minus 15x plus 7, and x is our character value, and then we do that mod 16 or something, so we get back to a nice small set of numbers to work with. So our algorithm hash is the encoding algorithm. A lot like an encryption algorithm. So somewhere along the way, there's a good chance you would have already seen encryption algorithms. You had to have at least 3 programming classes by now. I'm going to go ahead and count this one because we're only 2 weeks in the end. You've had to have at least 3 programming classes, and as big a deal as security is in 2022, there's a good chance you've already seen an encryption algorithm, right? So kind of the same thing, only it's not a secret. We're not we're not trying to make it a secret to keep people out. We just want a number. That sort of idea. And then we end up with a table. Oh, good. I didn't run off the. So first thing that happens is the computer looks through here, looks at how big our data set is. Three things. So we need a table, and it's going to set up a specific size. That's almost always going to be bigger. I'm just going to fill in the picture I have here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that looks nice. 9. So we had three elements. Let's make a table with 9 rows. That'll work for us. Then our data is just going to go straight over there. Right? We don't want to mess with our data, so it's going to go around, bypass the hash algorithm, and the data is going to go straight in there. But the keys are the ones we're worried about. So like our age, we'll take this one, send it over to that algorithm, and stuff happens on the way to an algorithm, right? We change that around a bunch of times, use those Unicode values as numbers, run through some complex math equation. And on the other side, we get a nice small number. So maybe we got a 4. We turned the word age into the integer 4 from whatever our algorithm was. It's a big complicated thing. So now that data point 32 is indexed by the number 4. And then we gain a bunch of efficiency. And hopefully at this point, you already see why that's going to be really good for things like Twitter, where we have billions of people. But originally it was 140 characters. Now there's no limit of characters and pictures and videos and all sorts of stuff. But billions of people, the data set is massive. And we need a way to connect them all together. And all of those things, to connect them together, we use the hashtags. We come up with a word, which is just a key for a dictionary. And then that turns into a number so that when we're talking about like billions and billions of tweets, it really cuts down on the size needed to index that collection. The same thing, like the next one's a weight. We grab that and it passes through whatever it does inside that hash table and comes down to 5, 6, 7, 8. We get an 8 out of that to index that value 133. So we get back that efficiency we lose when we use a dictionary instead of something with numerical indexes. But as far as the code, anytime we're working with it, and same thing with the height, we come over here and it goes through here, and maybe it goes up to 0.2. We get back that efficiency we lose when we work with strings, but anytime it comes back to the human form, we're working with the strings. So we get the ease of working with strings, but the efficiency of working with integers. And that adds up a lot. These 3 data points, if we use integers, it should take 96 bits to index all of them. But 2 of those 3 required 96 bits just for the index. So more than double it. Yeah, actually that'd be 150% increase because the other one was half that size. So 150% increase to use that just on 3 strings. Okay? And those are small strings. Those aren't very descriptive. Right? As it gets better and better keys for us to use in our code, that's going to get worse and worse and worse as far as efficiency on the computer. So we just need some sort of complicated math scheme to turn that into an integer, and then that just becomes rows in the table. And then the computer, then it's a jump table. Assembly language, one of our instructions in every assembly language is jump. So then we can just say jump to number 8. bam, we got that data, bring it back and we know which, we can grab the data really, really quick. Jump tables are one of the most efficient ways for a computer to process. And to kind of explain that, I'm going to pull up a picture of CMOS chip. That'll work. CMOS IC. So this will work. So on this chip, here's a ROM chip. Am I sharing my screen? Nope, sorry. I forgot to hit the share screen button. This one will work. So here's a ROM chip. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's 24. So this is going to be a 16-bit ROM chip, and then there's 2 clock signals and an enable, and there's some other stuff. But 16 pins on this chip carry electrical signals or data. And that's what we're writing when we're talking about binary code, right? So to access these, sorry, I said 16 pins. It's going to be, this one's going to be for 8-bit data. I was looking for the ones that I normally use, but I don't see them. I don't see a picture of it, but for like a ROM chip or a RAM chip, we have 2 sets of 8 bits. One of them is an address, and one of them is the data. So we feed in an address in binary. Maybe it would be better to just draw a picture. This is why this is one of the best shapes for jump tables, or one of the best things for a computer. I'll draw the picture in red. So we have this chip, and I'll just do 4 fat. I'll do 4 because that's plenty enough to draw on a board. So here's our 4 addresses, and here's our data. And we'll just do 4 bits on the data. So to get to any spot on that, any particular thing on that RAM or ROM chip, what we do is feed in the address we want. So if we want what's stored in, say, bit 11, we would feed in 1011. Right? So we would just automatically turn on all those signals and leave off this signal. So that feeds in at 11, and then from the wiring inside, we automatically get the data that's stored at that address, which is what's going on here for an 8. If we want what's stored on number 8, which I guess I would need a couple more bits of data. We feed in address number 8, and this is the speed of electricity on our bus signal, so it's not serial lines like USB where we send it 1 bit at a time. We send all, I went through 4, but all 8 bits in at once on an 8-bit bus. And we get that address, and then coming out the bus, we automatically get the output. 128, what do I need? 5 more? 0, 0, 0, 1, 0, 1. We automatically get that out at the speed that electricity moves across a 1/4 inch of silicon. Right? A 1/4 inch when that silicon is wrapped in plastic. So really, really quick. So we get that back. We have to turn those strings into integers to get it that fast. And when it gets big, like the reason you would have heard hash long before you took any computer classes, right? From Twitter, when we get data sets like all of the tweets that people made today related to, I don't know, probably Elon Musk is still up there, right? I haven't paid attention to that in Twitter. I laughed at it the first couple of days and stopped paying attention to it. But I assume there's still lots of chaos going on there. But lots of all those hashtags with his name, it goes through an algorithm, turns into a number, and then we can talk about how fast it is based off the electrical circuit itself. It's not like a tree where our computer still does a bunch of processing and do an ALU and switches things to two's complement and make comparisons that way. It is just electricity straight passing through a circuit. That kind of speed advantage for our data retrieval. That's what a hash table is. And you can see that in general, we're just storing our data, and all we need is a complicated math formula. The problem that arises, and why I say complicated as opposed to the normal complex, I was trying to use those words separately. Complicated means hard, complex just means lots of levels. Is because if we're not careful, this picture quickly loses realism, and we might end up with two keys that both give us the number 4. We call that a collision. Two things ended up that should be on the same row of that table from our algorithm. So our hash algorithms have to be kind of, they have to put out a unique number. And they have to do it for billions and billions of indexes. It's not like we only have to find 10 unique numbers, like the example drawn on the board. We have to all the hashtags on Twitter. We have to have a math formula complicated enough to give us a unique value for every possible hashtag that people would think of. And there's a lot of room for collisions there. So that part does get kind of complicated. But hopefully the core idea of it seems logical. And you've probably heard that word since before you took any computer classes. So I wanted to make sure and at least do a quick rundown of what's going on with that. But again, it's one of those, we're not going to see that advantage till long after school, because anything we do in school, we're not talking about that many extra bits for keys in a dictionary. Right? If it fits in the time constraints of a classroom, we can only type so many dictionary keys in a semester class. To the point that with a couple gig of RAM, any modern computer could handle it with no problem. It's for when things get really, really big, like all of the tweets on Twitter. There was one more that I wanted to talk about. And the reason I want to include it is because it's sort of it's what's used in our best NoSQL sort of databases. And that's a graph. So you probably heard the word graph in math class. Usually used to describe a plot. The origin of graph was the question back in the 1600s, maybe 1700s. This town in Germany had 5 bridges of Königsberg. And the question is that a bunch of rivers met in the same place, so that it was basically like islands. And there were 5 bridges, and the question came up of, can a person visit every island without backtracking across the bridges, with only crossing every bridge once? The answer was no. We have 5 points. Uh, 5 points and need to connect these 5 islands. There's no way we can get through all of them without backtracking at some point along the way. And that's the origin of what a graph is. We have are nodes all connected with edges. So those who have seen some 3D modeling, that uses vector graphics use 2D vector graphics do it as well. We don't see it as much there. It's hidden in the background. But the nodes connected with edges, and we specifically define what all our connections are. That's why it's nice for the non-relational databases, because we explicitly define how our data is connected, so we can optimize how a particular data set is connected instead of using those predetermined structured relationships like we have with the relational database. So when we have like the social media data that's all scattered, and if we tried to put it in a table, we'd have more empty cells than full cells. Those relationships or those connections from relational databases would be useless because of all the empty cells. We couldn't trace them around, we'd get stuck on empty cells along the way. So being able to define our own is really nice. Yeah, and that's what I'm going to write here. Explicitly define the connections between our elements. On the linked list, we had next element. That was the only option we had. On the tree, we have left and right. And all of our data structures have something like that, forming the connections. But here, we explicitly define them. And in graph theory, the connections are going to be called edges. And the elements are going to be called nodes. So we just set them up and define our connections exactly how we need them. What I have here on this first one. So five nodes, 3, 4, 5, and maybe all of these are fully connected. All 4 of those connect to each other completely, and then that one only has only connects to one of those. Or something with 4 nodes, and they're kind of like coming out of a central hub. We explicitly define every connection for the data set. Or maybe something with 6 nodes, 3, 4, 5, 6, that's fully connected. That's going to have a lot of connections. So this one needs to come out to every single other element. Same thing with this one. Then this one. And this one here, and then there. So lots and lots of connections. And there's some high-level math stuff. This has been actually one of the 2 highest studied things in high-level mathematics, in modern mathematics of the 20th century. The other one being dynamic systems, or chaos. People like to call it chaos. That's the interesting part of it. There's some non-chaotic dynamical, non-chaotic, non-linear dynamical systems, but nobody really pays attention to them because they're not interesting. And graph theory, there's a lot of stuff studied in modern mathematics, which doesn't show up until 400 or 500 level. The more advanced it is, the more useless it is. I once had a math instructor say that during the seminar class we were talking about. Did y'all know there's mathematicians are still learning new things about triangles? There's 3 academic journals that publish several times a year and do nothing but discoveries about triangles. But the last useful thing to know about triangles was what we call the Pythagorean theorem. And it was written on a cuneiform tablet, called Plimpton 342, 1800 years before Pythagoras lived. It said, as everyone knows, and it's like Pythagoras there. So 1800 years before Pythagoras, which was around 400 BC. So 4,000 years ago, that was cited as common knowledge. It's about the last useful thing about a triangle, but mathematicians still publish 3 journals. There's 3 journals that publish multiple times a year with nothing but discoveries about triangles. The higher the level it is, the more useless it is. I always remember that whenever they start to talk about that. So modern high level mathematics, but this one does get applied a lot. There's a lot of math theory that goes into it, but really from our perspective, for software development, computer scientists, doing the research and trying to put together a nice hypothesis that can be statistically validated through rigid experimentation. They need to worry about some of the high level mathematics and make those fine adjustments. As software developers, we just need to know that basic idea that we define those connections as we need them, the best way, how we see fit. And it gives us a lot of advantages, especially in non-relational databases. That makes the fastest non-relational database. As I was looking at different ones to show people, because the class here only ever covers SQL, and they keep adding more and more and more things to that class, and they barely even talk about SQL anymore because there's so many things they try to add into that one class. And I think you all probably know what I'm talking about. When you take that DBMS 110 class, and there's just so much stuff shoved in there, you can't really focus on anything. But the relational databases do have their limitations. And when I was looking around for one to show people of a non-relational database, because those didn't even get mentioned in there anymore. If anything, it gets mentioned that they exist. Certainly don't look at a couple of them. I found one that was closest to what was covered in that class, or what should be covered in that class. And the big selling point on it for people looking at big, powerful NoSQL databases is one of the main users of that uses it to deliver 400,000 targeted ads per second. That's a lot of data that needs processed, right? Targeted advertising uses everything they can find about you. All your social media accounts, your friends' social media accounts where they talked about you. All of that stuff needs processed through so that they can figure out what ads you should look at a given time. And they're doing 400,000 of them every second. That's a huge data set. So really the only thing that could possibly work for them is a graph-based database where they define all of those connections between the data explicitly to do that. The one I use is OrientDB. If anybody wants to look at one, OrientDB. I'll just pull up a picture, yes. So, a couple pictures here, you can see something like that. We have a bunch of, I can't really tell what that is on the screen. Well, it didn't zoom in on the picture. I was trying to read the labels, but I didn't. It like zoomed in on everything except the picture. Whatever that is, maybe it's different. I'm just going to go back to our classic example, animals. The blue are dogs and green are cats, and there's some connection between all of them and things. And they're defined explicit. All those connections are defined explicitly. You can see some of the different pictures. That is actually the interface for working with the database. I guess I can show that real quick. It's not 715 yet. And that was the last of the big 3. Or when it gets really, really big, things like this. There's a lot of data points there, and being able to control what data connects to other ones, it is really, really nice. I don't think I have anything set up for it if I start. I can check. I might have a previous example. If I don't have a previous example, we're probably gonna look at. Oh, whoops, LS. Right. Oh. Let's see. Um, okay, what's list out what's in, no, I did the wrong thing. Let's see. I know where to put it in Etsy. Oh, nope, nothing under O's. Well, actually, I can't remember where I have it on here. I know I would have put it in this folder. Those. Well, maybe I put it under, oh, there it is. Oh, yeah, that's slash print DD. What? Okay, this one. Pseudo, which one was it? Oh, yeah, that's the one I want. I haven't used it in a moment. Give me a minute to remember how to start it up or where I even saved it at. Example, looks like there's something there. Okay, yeah, so that looks like the sort of data we would get on social media. I can't remember what I was using this example for, but just random scattered data, right? There's more empty spots in that table than full ones. So instead of relationships between tables, there's specific connections. So whoever this person is, they did this person and formed a connection between them. So we define that specific edge between two people. dated at some point. And then this person also is neighbors with this person. And doesn't look like there's any other connection to that one. And then these two people are coworkers. So this person dated whoever this person is, and is a coworker with this person. And the one they dated is the neighbor of that. So we define all of those. So if I come over here and do select all from vertexes, V for vertex, it looks something like this. I don't have a regular mouse, so I have to. So see how all of our data points are still connected, but we explicitly define each one of those connections. If I click on it, this is the interface for editing the data and stuff. So instead of working with tables, we click on the nodes on the graph, and you see all the data we know about them, or edit it and add more, and that's actually our interface for working. This one is written entirely in Java, but it just to show how we would use those data fields. Each one of those is an object, and kind of a unique object. It's not a standard one size fits all. I could kind of go around. This first one looks like we know the person, their shoe size, and their age. But we also know that they happen to be neighbors with this person who drives a Mustang and went to Jeffersonville High School, who dated this person that drives a Toyota Corolla and likes the color blue, and happens to be a coworker with this person who lives in Sellersburg and works at an IT help desk. So basically, we found somebody that works at an IT help desk from somebody else's shoe size. That's the sort of data connections we need for targeted advertising. And that wouldn't fit in like the objects we've been making. It's a bit too chaotic for that. That's where the graphs start to show up. We find two connections that way. And if you're interested in using a NoSQL database, OrientDB would be my recommendation. They have decent documentation. Actually, they were one of the first ones I saw that they started embedding Udemy videos in their official documentation. Where's documentation? Full documentation. Oh, maybe that's not it. I'm getting started. Yeah. So they have Udemy. So their documentation isn't some website that you go read. Their documentation is a Udemy course. They were the first one I saw that did that. Starting to see it more and more. That's way better than reading through a book. Because Udemy is it's an indexed video. So they're all videos, but there's an index page like a textbook. Kind of a nice feature. But if you're looking for a good non-relational database to use, that would be my recommendation. That one was built entirely in Java as well. It was built entirely in Java, and they put a lot of effort into getting it as close to SQL as they can. It's a NoSQL database, but data analytics people know SQL. You all have to do SQL examples, right? So if you're doing something that's really close to SQL, you don't have to learn an entirely new language. So there was effort put in there, and it uses graphs, which is one of our data structures. And basically, this is what we need as software developers. There's other stuff for high-end research still. Mathematicians are researching graphs, so there's new discoveries. So then computer scientists doing all their formal research need to apply those new theories and stuff. But for software development, we explicitly define what it means to be a node and what it means to connect different nodes together. So I guess really the haphazard collection of data But it's still better than, but not randomness, not random haphazard. Like we would have if we just put everything in its own variable. And with graphs, that leads to one other one that can be useful, a spanning tree. Am I still on the video? Yeah. So spanning tree is a special type of graph where we minimize the number of connections. Graph where we minimize edges. So for example, if we had 3 nodes, that's nice and easy to draw on the board. We probably wouldn't do it as a graph. We'd probably just use 3 variables, but nice and easy to use. To fully connect it, we need 3 edges. But that's more than we need, because we can connect all 3 of those. I should do that in different colors. I got 3 colors. Red. Well, I'll just do it ABC. That way I'm not constantly changing markers because we're about to finish up for today. So to connect those 3 graphs, 3 edges is more than we need. We have A, B, and C, and we could connect both of them. A connects to C through B, or any version of that. We could do AC and CB. So 2 lines would be enough to do that. A, B, C. Is that all of them? Oh, yeah, one more. A, B, C. So there's 3 different ways we could minimize the number of edges there. And that grows very, very quickly. Is that right? No. 2 to the n minus 2 ways. Plus 1. There's that many ways. So if we have 3 graphs, 2 to the 3 minus 2 is 2 plus 1. There's 3 ways we can do it. If we have 4, A, B, C, D. Obviously, the full graph, full connection is going to look something like that. But that's way more than we need to connect 4 things. I'll just do a couple here. A, B, C, D. That would connect all of them. And I'm definitely running out of room, so I'll try a different color. That connects all of them. And notice what those 2 things have in common. How many lines are there? So when we had 3 nodes, we only needed 2 edges to connect it. When we had 4 nodes, we need 3 edges to connect it. So there's always 1 less. The minimum best we can do is always 1 less than the number of nodes. But if there's 4 of them, 2 to the 4 minus 2 be 2 squared 4. There's 5 different ways we can do it. We get 5 edges, 2 cubed 8 plus 1, 9 different ways we can do that. And you can see that's going to grow pretty quickly. When we get up to a reasonable data set, 20 things, 2 to the 18th power plus 1. We can ignore the plus 1 at that time. We can just have basically 2 to the 18th, which is a pretty big number. Right? Lots of different ways we can minimize the connections between those. So that's a spanning tree. So usually for software development, once we do those explicit definitions, we want to refactor it into a spanning tree. That way we don't get overwhelmed with the number of connections we made. Arbitrary. All right, 7:15. So That's a few of our most common data structures. Lots and lots and lots of them. Anybody heading on to a 4-year degree will have to take an entire semester about data structures to study the different ones explicitly. But the general idea is we get different optimizations for how we deal with that. You can think of it time optimization, or RAM optimization, CPU optimization. We get different things. So you want to use the one best for your situation. The time to develop is a consideration. That's why we usually fall back to that binary search tree, because we get really good efficiency out of it, and it's really easy for the programmer to develop. So that's a nice balance. A heap would be optimal, except for all of the work that it takes the programmer to develop a heap. It's usually not worth the programmer's time to develop a heap when one of the others will get through the stuff eventually. Like the extra work goes to a machine. The machine's never going to complain about it. So I'm going to find those optimizations, find the best way to work with your data, process it, connect things together. Examples of all the ones we talked about are in the book. We'll look at what the code is. A couple of them, make sure you take your time, study what's going on in each line. Don't try to read it like an English sentence. Make sure you understand what's going on along with those pictures that we're drawing up here. But at this level, just introducing it. So this is how we normally take a break. But at this point in the semester, I wanted to have a really short night. Well, obviously there's block time, so it's a good time to work and catch up on stuff. But my actual recommendation, 2 weeks left in the semester, my actual recommendation is take our extra time here and try and relax some. Because you all know what the last 2 weeks of the semester are like. It's fixing to get hectic. Take a few minutes and relax a little before we move into that hectic period at the end of the semester. Otherwise, as normal, I'll be sitting around until 8:50, ready to answer questions. Basically, just watching the email or the inbox on Every Learn. Text messages are the two things that make noise on my phone. The quickest way to get hold of me. If you have any questions, let me know. Otherwise, you all have a great weekend. And I will see you on Tuesday, and then we're starting our last module, which is odds and ends. We have some interesting, useful things to cover there. Any questions before we wrap up? All right, I assume 5 seconds to silence. If there's no questions, y'all have a great weekend. I'll see you on Tuesday.